paper towel,
Yeah.
use it to dry up because that thing is wet.
Alright.
It's hard to write on it.
Oh, I see.
So I use the paper towel to dry it after I wipe it. Yeah. It's easier. Sometimes, so I just found this Lysol wipes really works. Really
Oh,
good.
it's great to hear.
Sure.
Right.
Yeah, some of the black ones don't work. Some
Right.
might be old, these markers. You'll have to just go by trial and error
Gotcha.
on the ones that are, lying over.
All right. In order to do calculations on the probability of events, we need to have a mathematical environment in which we feel comfortable making these kind of calculations. And in probability, this is called the probability space. These are the three components of the probability space: the sample space, omega, the sigma algebra, F, and the probability measure, P. Now, each of these represent tools that we can use to understand the environment of the probability we're working with, hence probability space. So I will explain each of them in turn. The omega is probably the simplest to understand. Imagine for a moment that you have a die and you're going to roll it. I'll use this example because it's pretty illustrative for a lot of different kinds of ideas about probability. So we have a die. What are these 6 outcomes that are possible? Single dot, 2 dots, 3 dots, 4 dots, 5, and 6. Comma, 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 comma. Now you'll notice that I didn't put 1, 2, 3, 4, 5, 6. I instead put the dots. Why is that? Well, the reason is that outcomes in the sample space may not necessarily be numbers. And in fact, we'll have to do a mapping from these outcomes to a real number. But that comes later. That's not necessary for understanding this right now. In any case, these are our outcomes, right? So you would describe this as a set with these braces, and that would be omega for rolling a die, right? Each of these is an outcome of rolling a die. And in fact, this is all of the outcomes, which makes this a sample space. Each one of these outcomes is referred to by omega. This is little omega, even though it looks like a W, it's an omega, and that denotes an individual outcome. And so we can maybe helpfully label these omega 1, omega 2, omega 3, omega 4, omega 5, and omega 6. So these are our 6 outcomes. This is the easy part. Outcomes in a sample space. Got it, right? This is what we're operating on. Now, the sigma algebra is a little more complicated. And in order to understand why we need this, I'd first present to you a simple problem, right? Imagine that you have the real number line from 0 to 1. And I ask you, how do you get a number, let's say 0.5, right? If you pick a random number between 0 and 1, a random real number, what is the probability that it will be 0.5? 0, right? I mean, there are infinite numbers between 0 and 1. So the fact that you just randomly happen to pick 0.5, that seems so unlikely as to be impossible. And in fact, we would say that this is a probability 0 event. But clearly, you could extend this logic to any point within 0 and 1, and that would mean that no point has any probability, which doesn't seem to make sense. Our ideas of probability are kind of breaking down when we introduce these types of infinities, right? When we just approach, in a simple discrete space like this, it might be easy to imagine how we assign probabilities to each outcome. But that's not necessarily the case with an uncountably infinite set of outcomes. And so, for this purpose, we define the sigma algebra, which corrals these outcomes into a way that we can apply mathematical methods onto them, specifically the measure, which is the probability. But before getting ahead of myself, let me define the rules of a sigma algebra. So you first need to understand a set. A set is a collection of unordered elements. It has certain properties that are not necessarily important right now, but you will need to know the operations to do on a set. So for example, let's say we have a set A, right? You can do a union on another set B, and that would result in a set that contains both of their members. And in fact, for completeness, because technically this wouldn't be right otherwise, like this. And you could also use intersect, right? Actually, wait. Better to use the outcomes for this that we already have, okay? So you can imagine we have outcome 1, union, outcome 2, rolling a 2, and that gives you W1, W2. So this union has essentially put these two together. The probability of rolling a 1, probability of rolling 2, that's together now. And this is an event, right? Think of sets as events. We have the outcomes, and we can kind of combine the outcomes to create an event where either of these could happen, and that would satisfy this event, if either of these happen. Now let's think about the opposite of a union, which is the intersection. So we have a W1, W2, or I should say omega 1, omega 2, intersect omega 2, omega 3, and the result of that would actually be omega 2. And you can see this is an intersect because only the outcome, which is shared between the sets, is here. Now typically intersect doesn't have a lot of meaning for us. It is importantly the inverse of the union. And so you'll see lots of instances where unions will be flipped into intersects. But typically it is easier to think about how a set is described in terms of unions rather than intersects. Intersects kind of follows naturally from it. And then there's one more important operation that you need to know, which is the complement. And so this one actually has a motivating example. We'll say that we have the set of even outcomes, which is omega 2, omega 4, omega 6, and we want to find what are the odd outcomes. Oh, well, we can define that as E complement. And so complement means that all the outcomes that are not in set E, but are in the sample space omega, these are going to be part of O. And so that will end up being omega 1, omega 3, omega 5. So these are the three operations we need to know. Okay, so knowing these three operations, how do we get to this big F? Well, there are some rules around sigma algebras. So sigma algebras are generated from sets. A set like this would have a sigma algebra generated from it. And there's certain rules. So let's say that I have some set X, right? And I want to generate a sigma algebra. What are the rules for the sigma algebra? What is the set? Well, the first thing we want to consider is the power set of X. So the power set of X, P of X, that is the set of every set inside of X and all the unions of those outcomes, right? So you can imagine the power set of omega being, 1 and 2, 1 and 3, 1 and 4, 1, 2 and 3, 2, 3 and 4, 2, 3 and 5, every possible combination you can think of, that's the power set. And in some sense, this is a true sample space that, we'll consider for other purposes. But the important thing here is that this algebra is a subset of the power set, which means that every single element in X is represented in the sigma algebra. Now, what are the rules? The rules are 1, X must be in the sigma algebra. Kind of obvious, right? You're generating it from it, and so clearly it must be in it. This just means in, this little notation here, this little epsilon looking thing. 2, X's complement, any complement, sorry, I should say X's complement, any set A, so we'll say set A that is in X, A in X, then a complement should also be in X. So every set and every complement of a set will also be in X. And hopefully you can have some underlying intuition for this. if we're trying to describe the probability of events, right? If you have the probability, if you want to measure that an event did happen, you also want to measure the fact that it didn't happen. And then the third property, coming kind of from the same idea, is that it should be closed under union. Technically closed under countable union, but we'll not be specific here. Closed under union means that if you unify these sets, then they're going to be in the set as well, right? So if we have, for example, right, we generated from the set of even numbers here, then the union of all the sets that could have been made here would also be here. And so you can imagine, again, the combinations between these being part of the overall sigma algebra. Now, what this is useful for, again, going back to our motivating example here of the number line, is this allows you to mathematically describe certain uncountably infinite spaces, right? You're able to describe, for example, if you wanted between 1/2 and 1/4, you're able to describe this space as an event, as a set, as long as that set is a sigma algebra, and you can get a probability measure on it. So that's all you need to know about sigma algebras. This gets into, real analysis and algebra theory, and that isn't necessarily, it's kind of beyond the scope of probability theory, but hopefully understanding that, this is a way of kind of organizing some infinite space into a measurable space. That's the key to the sigma algebra. And so I'm using this word measurable, so let me define it a little better. So we have omega f, and this is our measurable space. So this is a space, we have outcomes, and we've corralled those outcomes in such a way that we can assign probability measures to each set of outcomes. And this f is a sigma algebra that we have chosen to generate here from this outcome. It might even be generated from omega. You can generate a sigma algebra from omega. And actually, I'm getting ahead of myself here. Let me talk a little bit about the sigma algebra, right? The basic sigma algebra looks like this. And what does this mean? The sigma algebra contains null and the sample space, right? And you can, very trivially prove, right, that actually this is a sigma algebra, right? We can see, if we generate it from null or omega, then it will be present in here, right? And in fact, any x will generate the null if you have its complement, right? For every a, its complement is in. These are complements of each other, and it's close to union. If you union them together, then you'll just get omega, which is in the set. And so this is the simple one, and you can keep adding more and more sets to this, right? And you can kind of see a symmetry. For example, you could generate a sigma algebra from E, and that sigma algebra would have null, E, O, and omega as part of its sigma algebra, and that would be a correct sigma algebra under which you could assign probabilities. Now, let's talk about assigning probabilities, and that's where P comes into the equation. And let me just clean this board up here. Right. Okay. Probability measure. We have this idea that we have some values here. And again, I'll repeat the dice example, right? These are our outcomes. We have, so this is our omega that we've generated, right? The sample space. And we can say that for convenience, that these all represent individual outcomes labeled by omega 1 through 6. And we are saying that there's a sigma algebra here that we are considering, right? Now, we could choose to define a lot of different sigma algebras on this set. I'll pick the one that I used earlier, which is even and odd. So if we generate a sigma algebra that is generated from E, which we defined earlier, then we're going to get null, omega. These are part of any sigma algebra. We're going to get E, and we're also going to get O. And intuitively, you can see here how you might assign probabilities to each of these values, right? What is the probability of the null set? Well, it's 0 because nothing in the null set can happen. It contains no outcomes. So we would say that the probability measure of the null set is 0. Correct. What about the probability measure of the omega of the entire sample space? This is actually part of the definition of a probability measure. It's very important, which is that the probability measure of the omega equals 1. And this is an important property for reasons that we'll see later in determining, what is the kind of base case? What is the number that we're basing everything else on? And everything gets, pieces taken out of this 1, but the 1 is the whole, and the omega, the sample space, is 1. What about the probability measure? And again, I'm using probability measure here because we're talking about sets of outcomes. And so we're applying a measure on that set of outcomes. So the probability measure of E, what is that? Well, we know if this is a fair die, that we're assuming that it's a fair die, that the individual probability of having any one of these things happen is 1/6, right? And we can also kind of easily deduce in our heads that the probability of getting an even number is 1/2. And so I'll just put this here for now, 1/2. And the probability measure of O is also 1/2 for the same reason. There it is, the probability space of a fair die when we're considering the outcome being even or odd, right? Now notice here, we're not actually interested necessarily, right, in the outcome of any individual one, right? We could have constructed our sigma algebra in such a way that's generated from each individual outcome and get all the different outcomes. It'd be too much for me to write. But just constraining it here, we're measuring the even and odd. And you can see here how a probability space is useful in constraining what we're thinking about. Even though we are rolling a fair die, and there might be these other things to consider, we are constraining our probability space to the sigma algebra generated by the even and odd set, and the probability measures on that. So we've seen this usefulness, right? I finally demonstrated to you this is the probability space. But there are some rules around probability measures that we need to keep in mind, right? So one of them, I've already stated, is that the probability measure of the omega, the sample space, is 1. Additionally, for any set A or B that are in F, remember this is the context that we're living in, is the sigma algebra, right? If we have probability A plus probability B equals probability A union B, assuming that A and B are disjoint. And so what this word disjoint means is that they share no elements in common. And hopefully, intuitively, you can see how this makes sense. For example, even and odd are disjoint sets. They don't have anything in common. This one has 1, 3, 5. This one has 2, 4, 6. The probability of having them each is 1/2. If you add them together, you end up getting the whole sample space, which is omega, the probability of which is 1. And so we can demonstrate this same idea here. So now that we have our probability measure, right? This is the property that we add up unions. And actually you can see how this is useful because once we get the probability of any individual member of a set, we can add them together to get the probability of any event. And actually this is how we construct, like I said before with the motivating example, the real number line. Our interest here is finding some way to measure the probability between these two places, right? And so we can actually do this by sort of adding up all of the events that occur in this. Now, how do we define those events, right? Actually, this is a little bit, off topic maybe. You don't really need to understand anything else than that probabilities get assigned to real numbers. But if you're interested, because it's an important topic, we can create the Borel sigma algebra. The Borel sigma algebra. And you'll often see this term in probability, so it's important to understand what it means. The Borel set, sigma algebra, or the Borel set, as it's also called, describes the set of all closed intervals on the number line, the sigma algebra of that. So you have the Borel set and the sigma algebra from the closed intervals on the number line. Now, closed intervals, right, to give you, some idea of what we're talking about here, it could be 0, 1, it could be 0.5 to 170, any kind of interval like that, right? This is an interval. And we have all the intervals, the uncountably infinite number of them, and we're packaging them inside this Borel sigma algebra. And magically, through the power of probability theory, that allows us to take a measure so that we're able to look at the 0.25, 0.75, we're able to look at this interval, and we're able to assign a probability measure to it. Now, in this specific example, now this gets into distributions, right, which is a little bit, farther on from what we're talking about right now. But if you took the uniform distribution on this, as we did, everything between 0 and 1, then you could very easily calculate the probability measure as just being this minus this, which is 0.75 minus 0.25, which equals 0.5. Now, intuitively, you know that this is to be the case, but I would just provide a rigorous mathematical way to obtain this using probability measures. And this becomes important because we can use this in more advanced ways to compute probabilities of things that are not necessarily intuitive, particularly stochastic processes. This is why stochastic calculus relies on probability theory, because we have stochastic components to our regular calculus. We need to be able to categorize them and understand them and measure them. And that all comes through probability theory and measure theory. So having understood the probability space, again, I'll write it out for clarity. We have the sample space, omega. We have the sigma algebra, F, the kind of addressable, measurable space. And then we have the probability measure on that measurable space. And this is the probability space. Thanks for listening.